Hello again, everyone, and welcome back to our course in college algebra. Dr. Tom McNamara here, and we are going to continue our discussion of graphing using transformations. You will remember in the last video that we examined a library of functions. Now, we had already seen a couple of them. We had already seen the absolute value functions graph, which is a V shape, and the graph of y equals x squared, which is a U shape called a parabola. And we added graphs of the cubing function, x cubed, and the square root function. So let's talk about how we can use that. So here's an example we're going to work on. Graph y equals the square root of x plus 2, and then there's a plus 3 on the outside. So the basic graph that we start with is that of y equals square root x. Now, I mentioned in our last video, not only do we need to remember the basic shape of our graph, we needed to remember some anchor points. One of the anchor points was 0, 0, 1, 1, and 4, 2. Okay, these are all on the graph of y equals square root x. So we get that because this formula involves the square root. So the graph of this equation is going to be the same general shape as the graph of the square root function. Now, we look at the formula and we see what changes have been made. Well, we see that x has been replaced with x plus 2. And you'll remember that shifts you 2 units left. And this plus 3 on the outside will shift you 3 units up. Okay, remember the inside kind of works a little bit backwards of what you might think. If you replace x with x plus 2, that moves you 2 units to the left. If you replace x with x minus 2, that will send you 2 to the right. Okay, so let's see what happens to our anchors, right? If I'm at 0, 0, and I go 2 left and 3 up, I'm at negative 2, comma 3. 2 left, 3 up. I'm at negative 1, comma 4. 2 left, from this point, 2 left would be x coordinate of 2, 3 up would be 5. Okay, so I use that information to draw my graph. I'll put it over here. So let me get started with these points here. These are the new points. These are where the anchor points got moved. Okay, negative 2, comma 3. So negative 2, 1, 2, 3. That's a point on my new graph. Negative 1, comma 4, which is right here. And then 2, comma 1, 2, 3, 4, 5. Okay, and we connect these with a nice smooth curve. And that's our graph. Okay, so not a ton of computation going on here. The whole point of using the technique of transformations is that you can get very accurate graphs without a lot of number crunching. I want to show you some examples on MyMathLab. So let's bring up the window capture, and we'll get rid of the document camera for now. And we don't need that. Okay. I'll stay in the picture for now, though. Let me make this... Ooh, okay, I'm not sure I like that. I can't make that part smaller, can I? Okay, this looks like we can kind of see it. All right, so the question on MyMathLab is asking us to use transformations to sketch the graph of f of x equals x minus 5 quantity cubed. Okay, third power function. So we know the basic shape. And we can see in this function, x has been replaced with x minus 5. So that is a shift of 5 units to the right. Okay, and let's draw the graph. Okay, it pops up right there. It's asking us, when you're using this tool, you click the shape that you want. Okay, this is the cubing tool. And we decided we were going 5 units to the right, so it's there. Oh, okay. Vertical shift is 5 units to the right. No. Oh, shoot, sorry. Silly. Clear this. Moving 5 to the right is a horizontal shift, so just click anywhere. The horizontal shift is 5 units to the right. We will save that. Okay, notice it puts our picture in there. I can disappear for right now. Bloop. So the graph has been drawn in there. We told MyMathLab where to put it. We click check answer, and we got it. Wonderful. There's another kind of question that I'd like to show you here, and it's this one right here. Basically, it's a backwards question. These guys are all giving us graphs and asking us what the equation looks like. So let me pop out this graph here so we can see it. We notice a V shape, so we know what function we're dealing with. We remember that for a V-shaped graph, we would have to be starting with the absolute value function. Ordinarily, the turning point is at the origin, but we notice it's moved 4 units to the left and then 1 unit up. And we know how to make that happen with a formula. What we do is, instead of absolute x, like this, instead of that, we want x plus 4. Remember, replacing x with x plus something actually moves you to the left. If you replace x with x minus something, that's what moves you to the right. Now, we can see also the graph is shifted up 1 unit, so we do a plus 1 right there. We'll click check answer, and wonderful, we got it. Okay, so remember, all of the principles that we are learning work both ways. If, like this, you are given the function's formula, then you know the shape of the graph. However, if, like this, you are given the function's graph, then you know the formula involved. Okay, if you see this V shape, you know you're dealing with absolute value. And then, looking at the transformations, you can determine where to move the graph or what to do to the formula. It works both ways. I would like to do this, right? They give us just some verbal descriptions of a graph, okay? They tell us, okay, we have taken the graph of x squared and we shifted 2 units to the right and downward 3 units. And we can tell right away that would be this one. Replace x with x minus 2 to get a shift of 2 units right, and then put a minus 3 outside the function to move down 3 units. We'll click check answer. Got it. Okay? So, by simply generalizing what we know about the way transformations work with the absolute value function and the squaring function, we can get the graphs of tons of functions without plotting points. Okay, remember, plotting points is the way a computer would draw a graph. You're not a computer. Think about the shapes and think about the shifts, and you can get graphs very quickly and very accurately.